Hello, and welcome to another one of Ethan's engineering videos. Today we're going to be taking a look at Transport 1, Homework 4, Part 4, which is going to be an expansion and kind of a redirect off of our previous two videos. So if you watch them and you can remember back, you'll remember we talked about explicit differentiation and how we can, my runtime just disconnected, but it's now back. That was frightening. Backtrack for a second. It simulated how we could look at heat diffusion in a specific heat pipe, and how we could use that using a differentiated time and length along the bar and kind of iteratively simulate the diffusion of heat through that bar, because we'd have a bar at some one constant room temperature in thermal equilibrium. Suddenly we'd heat up the two ends and we'd watch the heat, the difference in temperature cause heat to flow through the bar through our rod, because it's a heat rod is what I titled our our Python page, and so that would allow our heat to diffuse. And the reason we can't just call it there and just be like, yeah, we can solve it, is actually because of some limitations that we discovered with that method. So if you watch the third video, you know what I'm talking about, but if you don't, really quickly, let's just pull up our graph of figure 1 once again. And you can see here we start with our temperature gauge, which is high at the two ends that are artificial temperatures, and low everywhere else, and slowly that equilibrium reaches until eventually we get a straight line connecting the two temperatures, which is what we'd expect. But that's with these dx and dt settings, and those contribute to our r. And if you remember, there's actually a limitation on this r, which says it cannot be, or it must be less than or equal, I hit that, EQUAL 2.5. And you might be wondering, well, what happens if we go beyond that? So the easiest way to do that is just to decrease dt. So if I add a 0 here, you'll notice our r goes down by a factor of 10, so it goes from 1/2, which is what it was previously, because this is, excuse me, that was a hiccup. This is 1, so it doesn't matter. So before it was dt, which was 0.5, divided by 1 squared, which was 1, obviously that'd be a half. Now with 0.05, our r is now 0.5. So if we run everything again, you're going to see something pretty shocking. Everything is a little bit funkier. And although that's not quite that crazy, just wait until you see this. Oh, my mistake. dt got smaller, which means that our r got less than 5 significantly. That's my mistake. What we want to do is we want to increase dx. That would also make it smaller. So what we want to do is we want to decrease dx. So we'll make this 0.5, right? So now 0.5 squared is 0.25 on the bottom, divided by 5, that's a r of 2. So let's run with this, run everything here. You'll notice we've got a bunch of errors, overflows, invalid values. What could that possibly mean? Well, if we take a look at our figure here, we're now reaching temperatures of 10 to the 294th power, which obviously is not good. And even if we were to focus on maybe like 75 iteration, we're in the power of 10 to the 62. So clearly something has gone wrong. This clearly is no longer a curve from 0. This is some kind of a sine wave looking thing. And the reason for that is, again, as we discussed in our Newman instability analysis, because fundamentally, based off of Euler's equation and Euler's Euler's transformations between imaginary numbers and sines and cosines, they're intricately related. And so the bottom line is, this is not stable. So if we wanted to use a really small delta x, we'd have to use an incredibly small delta t to make sure that we didn't break this less than or equal to 0.5 rule. So we're going to rerun this just one more time to get back to our normal graph. We can close it and discuss the solution to this problem, which is actually, instead of explicit differentiation, it's implicit differentiation. If I misspelled implicit, please don't mind it. So what is implicit differentiation? Well, if we take this formula right here, and instead of solving for that single value of our focus point in the future, we instead first change these to u's, because we're going to adjust how we actually look at this equation, but instead solve for the average of that original equation. We actually find that this equation holds true, which is that we can actually solve for 3 points in the future, our focus point and its two adjacent points in the future, from the 3 points, our focus point, and its two adjacent points in the past. But now using this factor of u instead of r, where u is equal to, and I'm going to write this out as code so that we can see it, u is equal to kind of the same thing as r, which is dt times diff divided by dx squared, but now this is going to be 2 times dx squared. So this is our new equation that we're using. This is implicit differentiation. Again, the algebra to get here is fairly simple. We did it in class. I'm not going to bother boring you with it here, but essentially we take our original function and we take the average of both sides from the past and the future, and eventually it works out into this form right here. So in this way, obviously our equations are more complicated. We're no longer going from 3 points, our focus and our 2 adjacent, to our focus point in the future. It's now 3 temperatures to 3 unknown temperatures. So how do we solve this? Because we can no longer do what we did previously in its entirety, because that won't solve everything. And the solution is to use this third function that you may have saw us import in part 2, which is this scipy lin alg solve banded function. So what exactly does solve banded do? We can take a look at it down here. Solve underscore banded. And if we look, it takes a matrix in this shape right here. This is a diagonally shaped matrix. We have A0, A1, A2, A3, A4, A5. And down here we have 0, 0, 0, 1, 0, 2. And as you can see here, we are focusing on how these follow each other over time diagonally. So what we're going to need to give it is the number of non-zero upper and lower diagonals. So based off of our central diagonal, which is going to be the entire length of our array, we're going to have 2 diagonals that are slightly offset one side or the other that represent the bands that are following along it, right? So if you think of 3 stripes and then you were to rotate them diagonally, of course they'd be a little cut off by the rotation, but again they're going to be notated there. Our first thing, which is going to be a tuple that represents that. So I'm just going to put a little tuple here for now. The other things we need is to actually solve the matrix equation of AX is equal to B. So how exactly do we solve this? Again, assuming that A is a banded matrix. Well, if we look at this right here, and we were to say convert it into a linear algebra problem, we'd actually see that this right here is our array of unknowns, and right here we have our array of coefficients. So if we were to write that, it would be minus u times 1 plus 2u times, and minus u there would be our regular array, and that would be matrix multiplied with our array of unknown temperatures, which just for shorthand I'm going to call T1, T2, and T3. And as you can see, that would be equal to all this stuff on the right side, which again, this is the information that we do know because it's the current temperatures across those 3 locations, and our unknowns are here. This is the x we're solving for, and this is an array, a banded array, but still an array of coefficients. So that's what we're going to be inputting here as our a is going to be this right here. This is what we're solving for, our x, and this is going to be our b term, which is kind of what we did before. So in order to get to the solve banded, we're going to need to set up these coefficients as a banded matrix and work on that. So I'm going to make a new array called future banded. That's a caps lock. There we go. Future banded. It kind of remembers because I ran through this once or twice before just to make sure I knew what I was doing going in. So our future banded is going to be a new matrix. So we're going to do np.full. It's going to be full of zeros, but we first need to put in the size, right? So the shape, what's the shape going to be? Well, we're going to return a tuple, and the tuple is going to be, well, how many bands do we have, right? So we have our central band, which is our 1 plus 2u, and then we have our 2 on either side negative u bands. So it's going to be 3 bands. And then how many integers are in, how many coefficients are in each band? And if you think about it, all of the coefficients belong to temperatures that are changing with time. So we know that there are n segments in our array. Since we're going to just be reusing this, I'm probably just going to, this is already ran, so the only thing that's different is the use. So this is already run, so we already know what n is. So n is how many things we have, and then we subtract the 2 that are not going to change. And that should tell us how many temperatures we need to change. And so what's our fill value? Well, we're just going to use 0 for now, because we don't actually know what this is yet. So look at that. We'll have our future banded right here so we can see it. And we see we have 3 arrays, each here with 3 bands, and each one containing zeros right now. However, we're going to have to fill this, obviously, band by band. So our first band is going to be a negative u band, So we're going to do full banded, not full, future banded, and we're going to want to do the first row, so it's going to be 0, colon. And then as we discussed before, it's a diagonal, so that means we're taking this array right here that you see on screen, and we're rotating it by 45 degrees to get a diagonal matrix. And so because we're rotating it around that, we know that some things are going to get cut off by the fact that we're in a square matrix, we're going diagonally. So what that's going to look like is this 0 band right here is going to be, its first indice is going to be chopped off by the wall. If you think of this as the one below that matrix, right? So we have 2 lines right here, and they pivot down into the wall. Now if we do a cutoff vertically to where this first one ends, I don't know if you can see it, we do a cutoff here, obviously my wrist right here would be cut off, and that would be the first term here. So we're going to do it from 1 to the end, are going to be filled with the value negative u. So if we run this again so you can visualize it, you can see that our first thing right here is actually missing negative u, and that's totally fine. So we're going to do the same thing for the end, because that's also a negative u. However, that's going to be our row 2 right here, because it's going to be the final band. And instead of being from all of them except the first one, it's going to be all of them except the last one. So we run this again. So you can see here now we kind of have a mirror complement, because again, if we were to cut this off, this would be cut off by the floor, and this one would be cut off by the left wall, if you think of it that way. So now we just have to fill the middle one, which we're going to fill in its entirety. So we're going to do row 1, the whole thing is going to be equal to 1 plus 2 times u. So we run this, and now we have a full banded array. Right there. I kind of wish there was a way to show them all in line, but it is what it is. So you can see here there's our rows of negative u's, a row of negative u with one missing at the end, and this one which represents the whole diagonal length of our matrix, which would be 18 in this case. So now that we have our banded arrays, and we have our u right here, what we're going to need to do is we're going to have to do the same thing we did over here. So I'm just going to copy and paste this, but obviously we're going to need to use this solve banded code somehow before we plot. So I'm going to just make some spaces up here, copy and paste our solve banded in right here. Oh, there's an S missing for some reason. There we go. So this is our solve banded. So what are we going to need to do to make this actually work? Well, obviously, whatever our solve banded spits out is going to be the 3 temperatures we're looking for. So this is what we're going to actually update our solve banded based off of. I can delete this now. So we're going to do, obviously what we're updating for is t from -1 to 1. So that's going to be equal to our solve banded output. So right now what we're doing is we're modifying our temperature here. So we obviously don't want to do that anymore, since we're going to do that in our solve banded step. And we're going to modify this to use u instead of r, because again, we're working with the average version now. So this is still calculating the same things. This still calculates, I can get rid of u as well. This still calculates the change in our inner temperatures. However, if you notice, this is only calculating it for those points, and it's not at all really considering, I'm trying to think of what the word is. It's not considering the outlying points, because again, we are not changing t anymore. So we're going to create this new thing called b, because again, if you remember that solve banded uses an a and a b, right? A is the one on the left side. We made future banded, which represents our a, so we can actually pour that in right now. Future banded, and then all we're going to need after that is our b. So we're going to call that b right there. And of course, we know that L and U is the number of lower and upper matrices in matrix diagonal form, which is going to be 1 and 1 because we only have one of each. So I'll just put that in there. So now our solve banded is done actually, but our B is not. So our B is not finished. And as I said before, the reason for that is because of the cutoffs of this system. This B only represents, it represents, or it doesn't represent, I guess would probably be the more succinct way to put it. Doesn't count for t at 0 and -1, right? So those outlier values aren't really modifying the inward set at all. So what we're going to do is we're going to do b at 0 is going to be equal to b at 0 plus And remember, we're going to add in so again, if we're focusing on the last point there, yeah, so again, for the same reason that our future banded arrays are missing these certain areas in here, because again, this represents our, I'm trying to find like the correct words to explain this without having like a visual example in front of it, which is being kind of difficult. Essentially, we're going to add positive u plus u times t of 0. And we're going to do the same for our final point down here. Oh, tab. It's going to be t of -1. It's going to be b of -1. It's going to be b of -1. And so basically, just because of these gaps right here are the same reason that we need to update this, because again, this doesn't account for those endpoints right there. So I believe with this, everything should run theoretically. I'm not entirely sure if it'll be correct. 0. Okay. What does that mean? This is a 318. You use an 18 type. This should work theoretically. We'll see what it looks like. Fig 2. This should be Fig 2 as well. So we'll fix that as well. This needs to be Fig 2. We want to make a new figure here. Fig 2, Fig 2. Run U. There we go. Okay, I don't know why that took so many darn tries. But now as we can see, we've gotten the correct answer. I was like, I know I'm typing it in right, I just don't know why it wasn't applying there. Because obviously, this is spitting out an 18 size matrix, and this is a 20 matrix, but we're only doing the edge pairs. So there's no reason it should have not been working. But I really didn't do anything different. I mean, you guys watched me, it's all recorded, it's all on video, nothing changed. So I don't know why it was misbehaving like that. But yeah, so it's worked, thankfully. The solution has obviously not got rid of that, but so yeah, it very clearly does work. So will this still work in the other cases? So if you remember with this, when we ran this, why would you say it's not copy? And I think so. I think all sorts of copies, right? This is another issue. I think it's copy. It's not that's fine. You don't need to really do it. This. Yeah, it's doing all this weird pop-any stuff. I really don't know what's going on today. Anyway, Fig 1, we get this answer. Reset T. Run. This has already been run. This has already been run. Get rid of U, because that's clearly not helping. Run U to get Fig 2. Run Fig 2. We get the same picture. So obviously it works. It gives us the same result. So now let's test where we go wrong. So if we made dx 0.5 on this, and move Fig 1 to the end of this, just for convenience. Get rid of this. Show me Fig 1. You can see it goes out of whack. We compare that with reset T. Run U. I have to rerun. I have to reset U. That's probably why. That. There we go. Run fig 2. And you can see it has not lost its mind. So obviously this one, fig 1 failed, but the other did not. I'm going to, because I'm so annoyed with how this is working, I'm just going to define a new variable called t reset. And it's going to take in nothing, and it's going to do that. Or I can just throw that at the top here. T reset. I can throw it up here. T reset. It's really fighting me today. Oh, I have to do t is equal to. And then I have to return t, I suppose. I could probably make t global, but honestly I don't really want to mess with that. There we go, that's what we're expecting. I'll run it down here. No freak out. There we go. So clearly our implicit differentiation is not having the same issues that explicit differentiation does, and apparently my computer has been having all day, at least for this video, which is again very annoying, but I know what I'm doing. It's very clearly working. We're getting to our straight line answer. They look identical during cases where explicit differentiation works. But the reason for this is going to be in our follow-up video, homework 4.5, where I'm going to prove mathematically that this one doesn't have any failure conditions, just like in the previous video I proved mathematically that this one does, which is again bounded by being less than or equal to 0.5 for its R value. So thank you for sticking with me despite those completely random and unnecessary technical difficulties, not user error. I swear I haven't been mashing my keyboard with bananas or anything. But I thank you for sticking through me with those. My frustration was definitely palpable in the air for a second, but it's okay. We worked through it. But thank you for watching and sticking with me. I hope you guys have a pleasant week leading up to Thanksgiving, and at least for today, have a good evening.